Hello. Today we're going to look at two tests that will help us determine the divergence or convergence of series. Okay, so last time out we looked at infinite series and we were particularly interested in when they converge or diverge, and these are going to be a couple of tools that will help us determine that. Okay, so we're going to start with the integral test and we'll leap straight in with the theorem. Okay, so we're going to take the sequence of terms in our sum, the a subscript n here, and we're going to look at the function an here, where this an is a function. Okay, it's continuous, positive, and decreasing from 1 to infinity. And we're really just looking at kind of the equivalent function. So if the terms of our series are, let's say, 1 over n, the terms of our function will be just 1 over n as well. And what this theorem says is that if the integral converges, then the series converges, and if the integral diverges, then the series diverges. You'll notice here this is an if and only if condition. So really what it's saying is that the function and the series do the same thing. They both converge or both diverge. Okay, and let's have a little look at the theory behind why this is true. Okay, so here we have a graph. The blue line here is the function, the a of x, and if we integrate that function from 1 to infinity, of course we get the area underneath that curve. That's what a definite integral gives us. But also let's look at the red rectangles. Okay, each of those have a base of 1, and because they have a base of 1, the height of the rectangle is also the area of the rectangle. The area, of course, is just 1 times by the height. So the area and the height are the same thing. Because of each of these rectangles just touches the function, see at the left-hand end there, we know that in fact the area of each of these rectangles is the value of each of the terms of our series. So if we can take each of these rectangles, find their areas and sum them all up, we will get the area, we will get the sum of the series. Okay, so what does this mean? Well, let's look at these red rectangles. They're all a little bit higher than the function. So what this means is if we know that the function diverges, we can also say that the series diverges. They're a little bit higher here. Okay, so if we have a divergent function, we also have a divergent series. Okay, so that's half of it. Let's look at the other half, and we'll look at a different diagram. At first it kind of looks like all we've done is shrunk these rectangles down. If we compare here and then here, we just shrunk them down. But actually what we're doing is we're shifting them left. So we take this first rectangle and get rid of it, and then each of the subsequent rectangles we're just shifting to the left, and this gives us this. And now this says, well, we don't have the first term of the series, but we have all the rest. And each of these series terms summed up is now less than the integral from 1 to infinity of the function. And therefore, if we know that the function, the ax here, is convergent, we also know that the sum of the terms of the series is less than that, and therefore also convergent. Okay, so that gives us the if and only if condition. Conceptually, this is a little hard, particularly it seems like we're cheating somehow by making it below and above. But the actual application is pretty easy, and we'll see that right here. Okay, so let's take an example. We're actually taking the sum from n equals 2 to infinity here, and the only reason we start at 2 is because if we plug in 1 we get a 0 in the denominator. So we start the series at 2. And as a series, this looks pretty ugly, but let's think about it instead as a function. Okay, clearly it's the equivalent function. Instead of 1 over n natural log of n to squared, we've got 1 over x natural log of x squared. And we need to find that integral. Okay, now I don't want to spend too much time on the integral. If you want, you can pause the video right here and see how the integral works. It's a substitution. But what we find is that that integral equals 1 over the natural log of 2. Okay, and that's cool, but what we're really interested in is the fact that that's convergent. We don't really care what value it is so much as it's just convergent. And because this function converges, this improper integral of this function converges, we also know that the series converges. Okay, so whatever the integral does for the function, the series does as well. Okay, so we've done the integral test. Now let's look at the direct comparison test. And this is relatively straightforward. Okay, so we're actually going to take two series, the terms of two different series, the an and the bn. And generally we take the an might be something we know about, and the bn is something that we are given that's kind of similar, and we'll see in examples what we mean by that. In each of these cases, we'll assume that the an's are all less than or equal to the bn's for a big enough term. And what this now says is, if the bn's converge, in other words, if the larger one converges, then the an's also converge. The sum from n equals 1 to infinity, an must also converge. So essentially what we're saying here is if we're less than something that converges, it converges. And what part 2 here says, that if the an diverges, in other words, if the smaller one diverges, then the bn's, the larger ones, must also diverge. So we're looking for less than something that converges would converge, and greater than something that diverges would diverge. Okay, and let's take an example to see. Okay, so is the sum from n equals 1 to infinity of 1 over n squared plus 1 convergent? You know, it's a little difficult. I'd say we want to compare it to something that looks pretty similar but is slightly easier. And so since we have 1 over n squared plus 1, let's compare it to 1 over n squared. Okay, that's a little easier but very similar. Do you notice that 1 over n squared plus 1 is less than 1 over n squared for a positive n? And think about why that is. The denominator here is slightly bigger than here. Therefore, if the denominator is bigger, the whole fraction must be slightly smaller. Okay, and we know that the sum from n equals 1 to infinity of 1 over n squared converges. You actually might, right at this point, be thinking, well, how do we know that? We will eventually see why this is true with the p-series, but certainly we could find an integral here, take the integral test that we just did, and that would quickly and easily show that that converges. So here we have something less than something that converges, therefore this must also converge. But less than something that converges, converges. And we kind of flip this round now. What about the sum from n equals 2 to infinity of 1 over n minus 1? Okay, another nice simple example and a nice simple comparison. And now 1 over n minus 1 is greater than 1 over n. Again, this time the denominator is smaller, so the fraction as a whole is bigger. We saw last time that the sum from n equals 2 to infinity of 1 over n diverges. That was the harmonic series. And so we have something larger than something that diverges. So it diverges. Okay. So we have that that's a divergent series. Okay, well, that's good, but it doesn't always work. Imagine if you have something larger than something that converges, it doesn't really tell you anything. And in that case, we can use this limit comparison test. Here again, we're going to have these two different terms, the an's and the bn's. And we're going to focus mostly on part 1 here. We're going to take this ratio. We're going to take an over bn, and we're going to take the limit of that as n goes to infinity. And what we're looking for is that to equal some L, where L is a positive real number. Okay? And what this says is, if we can get this ratio to equal L, where L is a positive real number, then the sum of the an's and the sum of the bn's either both converge or both diverge. In other words, they do the same thing. Okay, so if an converges, then bn converges, and similarly, if the sum of the an's diverges, then the sum of the bn's diverges. There's a couple of slight variations here. We'll probably use this less, but if we can get the limit of the an's over the bn's to equal 0, then if the bn converges, so does an. And if we can get the limit of the an over the bn to equal infinity, then the bn diverges, and so does an. But I'll say we'll mostly focus on part 1 here, which says we can get that limit in such a way that it equals some positive real number, then they both do the same thing. And again, let's take an example here, and it looks very similar to an example we saw before. Let's take the sum from 2 to infinity here of 1 over n squared minus 1 and say, is that convergent or divergent? Well, let's try using our direct comparison test. 1 over n squared minus 1 is greater than 1 over n squared. The sum from 2 to infinity of 1 over n squared converges, so that's no good. That's the reason we have to use the limit, is that this doesn't really help us. Okay, we get something bigger than something that converges, that doesn't help. However, our choice is still pretty good, so we're going to use the limit comparison again between the 1 over n squared minus 1 and the 1 over n squared. Okay, so we're going to assign an to equal 1 over n squared minus 1 and the bn to be 1 over n squared And I say, note this is pretty arbitrary at this point. We could have had those the other way around. It really doesn't matter. But now we're going to take that limit, as we said. So we take the limit as n goes to infinity of that ratio, the an over bn. Okay, and we just plug them in here. So we get 1 over n squared minus 1 all over 1 over n squared. Hopefully you're pretty familiar with how to do this with fractions now. Take the reciprocal and multiply. So our limit becomes, the limit as n goes to infinity of n squared over n squared minus 1. Of course that just equals 1. A couple of ways to see that. L'Hopital's rule is 1. And since that is true, they do the same thing. And because we know that this one converges, we also know that this one converges because they must both do the same thing. Okay. Okay, so in terms of the limit comparison, in fact, and the direct comparison, the hardest thing really is choosing correctly the thing we would compare it to. We're always looking for perhaps the most important term here. So for example, if we look at some examples here, we have 1 over 3 to the n plus 7. The important piece here is just the 3 to the n, so it might be that we compare it to 1 over 3 to the n. If we look at, say, this one, we have an n squared and in the numerator and an n cubed in the denominator. So n squared over n cubed looks a bit like 1 over n, so maybe that would be our comparison. So again, I suggest maybe you pause the video now, think about what your comparisons might be, and then I'll show you what the comparisons are here and whether you should use the direct or the limit comparison, or either would work. Okay, so those are all our things we should compare with, and I guess I'll just throw in at the very end here whether they're convergent or divergent. Yep. Okay. And that concludes our work on the integral and the comparison test.